Very good morning, everyone. Welcome back to our second day to our third ISCPFM 2008, the International Symposium Current Progress on Functional Materials. So this morning we have a very special speaker. It is my honor to welcome Professor Russel Howee. Is that how you pronounce it, right? Professor Howee finished his BSc and PhD and DSc from Canterbury University, New Zealand. He is right now the chair of Chemistry Department of University of Aberdeen. And I believe Professor Howee is no stranger for us because he is the supervisor for our beloved Dr. Yuni Krishnandi, right? And without further ado, I would like to invite Professor Howee to talk about his speech or talk today about neutron spectroscopies for investigating geolite catalysts. And the floor is yours, Professor Howee.
Okay, I don't need the microphone.
Right, okay.
But my voice is a little bit sore, so I'm trying to lose it. So thank you very much for the invitation to participate in this symposium. This is my third visit, I think, to Depok, and I enjoy every time coming here. The hospitality is fantastic, so thank you for that. I'm from the University of Aberdeen in Scotland, which is about as far away from Depok as it's possible to get, which is why some Indonesian students like to come here. But they always go home again afterwards, right? So we're up in the north of Scotland, even north from further north than Edinburgh or Glasgow, more famous larger cities, and of course a long way from London. The university is very old, dates back to 1495. These are some of the old buildings on campus with some snow on the ground, so also different from Depok. Now I'm a spectroscopist. And all of my life, since I was a student, I have done infrared spectroscopy. But more recently, I've been persuaded to start using neutrons as an alternative to infrared spectroscopy for looking at catalytic materials. This is a collaboration I have particularly with Professor David Lennon from the University of Glasgow. Now, some of you will have met him. He has been here a couple of times in the last few years. So this is David, University of Glasgow, two of his students. Hantok, you will know, he's from University of Jambo and has spent time with me both as a student and as a postdoc. And then several people working with what's called the Catalysis Hub, directed by Richard Catlow. And then two people on the neutron beam lines that we work with, Stuart Parker and Ian Silverwood, and here are the funding bodies. In particular, the work is sponsored by Johnson Matthey, who are a UK company working in catalysis. So those are my acknowledgements. It's very much a collaborative project. When you use large facilities like neutron source, you need a big team of people. You can't do it all by yourself, and this team of people is important for what we do. Whoops. Okay, now why would we want to use neutron spectroscopy instead of infrared spectroscopy? After all, every lab has an infrared spectrometer. It's easy to do. Why would we want to use something as difficult as neutrons? And there's a number of reasons, which I've listed here. Most importantly for me, it provides access to lower frequency vibrations of adsorbed molecules that we cannot see by infrared. Here's an infrared spectrum of, that's a shadow on the screen. Here's an infrared spectrum of a dehydrated zeolite. And you see that below about, this is a diffuse reflectance spectrum, below about 1800 wave numbers, there are very strong bands due to the zeolite lattice. That means in practice, if we're looking at adsorbed molecules, we really can't see very much in this region because these bands are too strong. So infrared spectroscopy of zeolite materials, anyway, is restricted to the higher frequency end of the spectrum. Here are the OH groups, for example, in zeolite. which are easy to see by infrared. So a neutron, inelastic neutron scattering gives us lower frequency vibrations that we can't see by infrared. Second advantage is that in INS there are no selection rules. The only requirement for a vibration to be seen is that it contains a hydrogen atom. So all vibrations, all vibrational modes that contain hydrogen will be observed by neutron spectroscopy. That's because there's no quantum mechanics involved at all. There are no selection rules. I'll say more about that in a moment. Another problem we have in catalysis, if we try to look at used catalysts coming out of a reactor, particularly an industrial catalyst, like the ones we're interested in, it's often dark in color, often very black. And that's very poor for infrared spectroscopy. Very dark colored samples absorb a lot of infrared light. It's very difficult to get a good infrared spectrum from a used catalyst. Neutrons don't care whether the catalyst is new or old or anything in between. It's not influenced by the color of the catalyst. So there's another advantage. Another one is that we can apply the technique directly to industrial catalysts. We don't have to make any particular sample preparation. We don't have to grind the sample up to a fine powder. We don't have to press it into a disc. It's very easy. We can just take the catalyst straight from the reactor and run it spectrally. And the final point is that neutrons will pass through most materials. We don't need transparent windows. We can use stainless steel in principle, although in practice we tend to use aluminium as the sample container, but we certainly don't need to worry about having infrared transparent windows. So there's a number of practical advantages here to using neutrons for getting vibrational spectrum. But of course, as always, there are some drawbacks as well. One of the drawbacks is that it takes a long time to collect a spectrum because neutron fluxes are not very high, the number of neutrons involved is small, and typically for a catalyst sample containing a small amount of adsorbed molecules, it may take us 6 or 8 hours to collect one spectrum. Whereas infrared spectroscopy these days we do in less than a second. So the measurement is slow. We can't do in situ studies of reactions because we can't measure the spectrum fast enough. Secondly, spectroscopic resolution is not as good as infrared. Certainly not at the high frequency range anyway. The lower frequency, yes. So there's some trade-off in spectroscopic resolution. And then, because of sensitivity, we need a relatively large amount of sample, typically 10 grams. Now, some people would say that's an advantage, because if you're looking at a catalyst taken out of a reactor, if you take a very tiny sample for infrared, you don't know if that is typical of the whole sample. You maybe have to take lots of samples to convince yourself that you're seeing the correct picture. In the case of neutrons, we can take everything out of the reactor and get a spectrum from the lot. So we don't have to worry about sampling. Maybe that's an advantage sometimes. So that's inelastic neutron scattering, giving us vibrational spectra. A related technique, which we tend to do at the same time, although not on the same spectrometers, I must say, it's a different instrument, is quasi-elastic neutron scattering, which is called QENS. And this technique gives us information not about structure, but about motion. The molecule, particularly in a porous catalyst like a zeolite, how the molecules are moving. If they're moving on a time scale in the picosecond range, then we can get information about the nature of that motion and how fast they're moving from the QENS experiment. I'll show you some examples. But to extract the information, we've got to fit to theoretical models. So it's quite a tricky procedure sometimes to fit the data to a theoretical model. But in principle, QENS gives us information about motion. INS gives us information about the structure. Right, now here's a little diagram which sort of summarizes what we do. If you imagine a beam of neutrons encountering a molecule and being scattered, most of them will be scattered without losing any energy. This is the elastic peak here. This is a plot of intensity versus energy. It's a little bit like Raman spectroscopy. You know, in Raman spectroscopy, you shine light on the sample and look at the scattered light, and some of the scattered light has lost energy because it's excited vibrational modes in the molecule. The same is true with neutrons. Down here, at around about 1,000 to 10,000 wave numbers, or even lower than that, a few hundred wave numbers, we see peaks which correspond to neutrons which have given up some energy to the molecule in the process of being scattered. So that difference, the amount of energy they've lost, corresponds to a vibrational mode in the molecule, just like Raman spectroscopy. There's an important difference, however, from Raman spectroscopy because it's a quantum mechanical effect involving the polarizability of the molecule. Neutron scattering is not quantum mechanical. It's very simple. Neutrons are scattered by nuclei. This is really just like a billiard table. A beam of neutrons counters a billiard ball and bounces off. That billiard ball is a hydrogen atom that has a very large cross-section for scattering neutrons. In fact, the cross-section for hydrogen is much, much greater than any other nucleus. This is why neutrons are so good for looking at vibrations which involve hydrogen atoms, because neutrons are scattered very heavily by protons. They're scattered almost not at all by neutrons. We'll see an example of that in a moment. If, like me, you're interested in zeolite catalysts, then silicon and aluminium and oxygen are all in here, and their scattering cross-section for neutrons is negligible compared with the proton. That means when we look at a zeolite, we don't see the zeolite. All we see is the hydrocarbon or the hydrogen-containing species in the zeolite. An excellent sensitivity for hydrogen. Well, here's the scattering a little bit more schematically. So a neutron beam comes along with a certain wavelength and a certain momentum. And the momentum, of course, is a vector. So it has direction as well as magnitude. Unlike a photon, the neutron has a significant mass. So when it bounces off this nucleus here, it changes its wavelength, but also changes its momentum. So the scattered neutron has a different momentum from what it started with, that's K out, and it has a different wavelength. And so when we collect the scattered neutrons, we learn about two things. We learn about the energy or the wavelength of the scattered neutron and about its momentum. And we define Q as the difference between the outgoing momentum of the neutron and the ingoing momentum. And of course the wavelength or the energy depends on the vibrational mode that has been excited. So this is basically what the experiment consists of. Now there aren't too many places in the world that can do this. To do inelastic neutron scattering, you need a very intense source of neutrons. There are lots of nuclear reactors around the world that provide neutrons for research. There's one in Indonesia. But those neutrons are not sufficiently energetic and intensive to be used for inelastic neutron scattering. They can be used for other purposes like diffraction and scattering, but not for inelastic neutron spectroscopy. There's only a few places in the world which are these ones here. So in Japan, in the US, and in the UK, which have the capacity to measure inelastic neutron scattering spectra in the vibrational region. These are other synchrotrons, other neutron sources, which can in principle do it, but maybe not doing it very well at the moment because their neutron fluxes are not high enough. So it's a very restricted technique in terms of availability. And that's a problem, of course, because it means if you want to do this experiment, you have to apply for time on the spectrometer, and there's a lot of competition to get that time on the spectrometer. We use a neutron source called ISIS, which is the UK neutron source. It's located at Harwell, which is near Oxford. Antok has been there several times. There's too much detail here for you to see, But basically, how we generate neutrons, this is what is called a spallation source. That means that we generate protons in an accelerator here. This is like a proton synchrotron, which makes the protons go faster and faster. And when they're energetic enough, they're shot down this pipe here to a tantalum target. When protons traveling at almost the speed of light encounter tantalum, as a nuclear reaction takes place and neutrons are emitted. So a very intense source of neutrons, which come out at different spectrometers scattered around here. So in this collection of spectrometers, there are at least 3 that we can use for vibrational spectroscopy, 2 that can be used for Quench experiments. There's another beamline here which produces low energy neutrons for other sorts of experiments. But basically, I go to the next one, I think explains that a little bit more schematically. We have a proton pulse which strikes a target, generates neutrons, and then we have a spectrometer which can analyze here's the sample, neutrons hinge on the sample, we measure the energies and the directions and the momentum of the scattered neutrons. The sample is held at usually 20 Kelvin or even lower for maximum sensitivity. Because the protons are in a pulse, the neutrons come out in a pulse. So the repetition rate is a few hertz. So we're getting pulses of neutrons hitting the sample and then being scattered. And we want to collect them and measure their energies. Now, neutron spectrometers are not something you can go to the shop and buy. They are built especially for a particular purpose, and every spectrometer is different. There's not a standard model of neutron spectrometer, quite different from infrared. We use 3 at Harwell, one called Tosca, and you see it's the smallest of them. So it's about the size of a small elephant, and it has the sample mounted in a cryostat. The neutron beam comes through here, and then it's scattered back, and we collect the scattered neutrons and analyze their energies here. That's an example of what's called an indirect spectrometer, because it measures the neutrons only at one particular angle. MAPS is a much bigger instrument. You see the size of the person here. This is the size of a very large elephant, and it has a whole bank of detectors which measure not only the energies of the scattered neutrons coming from the sample here in the cryostat, but also their momentum. So this gives us a much bigger, more complete set of data for the scattered neutrons. Needless to say, it's easier to get on this one because it's not so popular. This is a better instrument. It's much more in demand. But the principle is the same. Firing the neutrons in, scattered from the sample, and we're analyzing their energies. Now, with a spectrometer like MAPS, we're collecting actually 2 kinds of information. What's plotted here is the intensity versus the wavelength or the wave number and the Q. Remember I said Q is the change in momentum. So when we measure the intensity at different angles, we're also able to work out the momentum. And so you get these kind of 3-dimensional plots of intensity versus wave number and Q. If we're doing spectroscopy, we're only interested really in the wave number. And so we can take slices through these plots to construct the spectrum. But what we're doing basically is collecting over a wide range of angles to give us more sensitivity. For Quench experiments, it's a much simpler instrument because we're only interested in measuring right around the energy of the incident neutrons. We're not wanting to extend the frequency range out the vibrational frequency region. So that's a much simpler instrument. The principle is the same. Neutrons coming in, being scattered, and we're only collecting neutrons very close to the energy of the incident neutrons. That's basically the elastically scattered neutrons. Right, well here's an example of a model compound in phenylsuccinimide showing you the difference between the infrared spectrum, which is red, the Raman spectrum, which is blue, and the neutron spectrum, which is in green. Now, of course, for infrared and Raman, there are selection rules. You know this very well. There are certain modes which are infrared active, certain modes which are Raman active, and some modes which are both infrared and Raman active. So when you compare the infrared and the Raman, you can see that. Also, the intensities differ a lot between Raman and infrared because of the selection rules. Raman requires a change in polarizability and the vibration. Infrared requires a change in dipole moment vibration. The intensities depend on how big those changes are. Neutrons don't care. They'll see every vibration involving a hydrogen atom. So, many more features. A lot of these will match up, of course, with the Raman and the infrared, but we will only see the vibrations that have hydrogen atoms associated with them. You'll also see what I referred to earlier about the poor resolution and high wave number. On this particular spectrometer, which was Tosca, the CH stretching region is very poor in neutrons. Much better to do infrared or Raman if you're interested in those vibrations. But down here, we've got all of this region accessible to us with neutrons, and we'll see all the vibrational modes that involve the motion of hydrogen atoms. I mentioned the difference between hydrogen and deuterium. Here's a nice little study from the literature which shows that. Take this molecule and then systematically start replacing the hydrogens by deuteriums. If you go from the bottom to the top, we've replaced all the hydrogens except the NH. And you see that means we've systematically lost pretty much all the vibrations from the neutron spectrum except the NH vibrations. This here, at about 800 wave numbers, it's not an NH stretch, it must be an NH bending mode. And that remains when all the others have disappeared because we've deuterated replaced those hydrogens with deuterium. That's just illustrating the fact that hydrogen is much more sensitive than deuterium. Well, I'm interested in catalysis, and the catalysis we want to study is the conversion of methanol to gasoline. This occurs over a zeolite catalyst. It was first introduced commercially in New Zealand in the mid-1980s. It was in New Zealand that I first became interested in studying this particular type of catalysis. That was 30 years ago. The chemistry is complicated, but basically what one does in this process, they make methanol from natural gas in the first instance. Then the methanol is converted. You can imagine it occurring through a series of steps to dimethyl ether, and light olefins, and then to gasoline. If you look at the product distribution versus the contact time of the reactor, then the longer that time, the more aromatics of the gasoline you get. So this is a commercial process for making a high aromatic gasoline. They closed it down in New Zealand a few years ago because the gasoline they couldn't find a market for. So instead they now sell the methanol rather than the gasoline. The process works very well, and in recent times they've started building plants like this in China, I think, to convert methanol made from coal into gasoline. So technology that works, but because it's complicated, it's not all that well understood. The catalyst is a zeolite, ZSN5. It's a three-dimensional network of pores. Other people have spoken about the zeolite already. Methanol goes in and gasoline comes out. Now, if you have this occurring in a fixed bed reactor, which is how we normally do the catalysis, then typically this is what the lifetime profile looks like. There's an initial induction period before the first carbon-carbon bonds are formed. So that's the initiation process for the reaction. Then we get a sort of steady state where the catalyst is converting methanol to gasoline quite happily. Steady state production of hydrocarbons, molecules coming and going, and then eventually the catalyst starts to deactivate, and that's the process that leads to the death of the catalyst eventually. Well, we're interested in all stages of this. The initiation is not appropriate for study by neutrons because it happens very fast. In fact, we use a technique I won't talk about today, but I will talk about tomorrow at UI, synchrotron infrared spectroscopy to look at this very first process, very first stage of the reaction. We use neutrons to look at the later stages, which are happening more slowly. So we've been applying neutron spectroscopy to look at the later stages of the reaction. Now, there's been a lot of work already on this, and under steady state conditions, it's widely believed that the mechanism is a complicated dual cycle, where you have a complicated mixture of olefins and aromatics in the pores of the zeolite, which undergo successive methylation and cracking to produce the gasoline range hydrocarbons. So this is the steady state of the working catalyst, and here's some of the evidence that's in the literature for this. Infrared doesn't work so well, actually, because as the catalyst ages, it gets darker and darker in color, and it gets impossible to measure infrared spectra from the catalyst at later stages. But people will use solid-state NMR, for example, to see some of these things. They'll also dissolve the zeolite and examine what's inside by GCMS, for instance. And the kinetics of the process are very consistent with this sort of autocatalytic dual cycle mechanism. Well, we use a reactor for preparing samples here, which contains about 15 grams of zeolite. We use a commercial zeolite, Johnson Matthey. It comes straight from the plant. It's not in any way adapted for academic use. And that goes into a reactor which looks like this, holds about 15 grams. That's mounted into a reactor system, which is a series of mass flow controllers for flowing different gases through the reactor in the furnace. And then we analyze the effluent by MS and GC. And we trap the heavy products for analysis afterwards by GCMS. Now, when we first started doing this, our hope was that we could take this reactor and stick it immediately in the neutron spectrometer. And we can do, but it's made of stainless steel to withstand the pressure and the temperature. And so the stainless steel is relatively thick. That means that we lose a lot of intensity if we have the sample in the stainless steel reactor. So what we've done instead is a rather cumbersome procedure, which Antok here got very good at, which is we take this reactor, seal it off, put it into a glove box, unload it, and put the contents into an aluminium can instead of a stainless steel can, so to do the neutron spectroscopy. So that's slightly cheating. It would be better to use this reactor directly, but the thickness of the stainless steel, for safety reasons, means that we lose a lot of intensity putting the neutron beam through. So we do load it into a can made of aluminium, which is thinner and doesn't absorb neutrons as much as stainless steel. Having done that, we then look at the catalyst at various stages in the MTG process. Now, the first thing we did was say, well, what happens to methanol at room temperature? If you put methanol at room temperature into zeolite hydrogen Y, to explain the spectrum a little bit, the bottom trace is the spectrum of the zeolite, empty. These are inelastic neutron scattering spectra, so they're like infrared spectra, plotting intensity versus wave number. Here's the spectrum of the empty zeolite Y, not Zenison 5, but zeolite Y. Here's the OH vibrations of the zeolite. So there are weak bands there, and an OH bending mode down here, but otherwise there's really nothing there. The zeolite doesn't contain much hydrogen, just a few hydroxyl groups. If we put methanol into zeolite Y, then we get the purple spectrum. The green spectrum on top is a sample of pure methanol. Now, when you compare these, they line up pretty well with one exception. These two bands here are OH bending modes of methanol. And you see, when it's absorbed in the zeolite, they are broadened out very much. Otherwise, the frequencies are about the same. That's the only major change. These have been measured with different spectrometers, so that's why the scales sometimes look a little different. So, the interpretation of that is that methanol is hydrogen bonded to the hydroxyl groups in Zenison 5. The hydroxyl bands have sort of disappeared, although that's a bit hard to see, and particularly the OH bending mode of methanol is broad. We do the same experiment with ZSM5. Here's the ZSM5 empty, there's the OH groups of ZSM5, here's the bending mode. Put in methanol. First sight it looks very much like the same as zeolite Y, but in this case we can't really see that OH bending mode at all. Now there's two possible explanations for that. One is that in this zeolite the methanol is dissociated, so we've lost the OH bond. That was the interpretation preferred by the people who first did this experiment. The alternative interpretation is that the methanol is more strongly hydrogen bonded, so that the OH bending mode is broadened even further than it was here, and so it disappears into the noise. So that's still an open question. Is methanol in zeolite ZSM5 at room temperature dissociated or not? Now infrared spectroscopy says it isn't, since it's there hydrogen bonded. Neutron says we're not sure. Now let's look at quens of the same system. Just a brief word about quens analysis. This is the elastically scattered neutrons from an empty sample container. So this is the background, if you like, of the spectrometer. And so we see a very sharp line here. This is energy here now in fractions of an MeV. Now, if you remember that this is fractions of a wave number. So we're very close to the exciting line here in the quens experiment. The vibrational spectrum would be away over there somewhere. We're not seeing that in quens. We're seeing just the elastically scattered neutrons. This is the resolution function of the instrument. And we can fit that with a Lorentzian. That's our background. Now if we look at the zeolite contained in its whole molecule, we see some broadening. And this is coming from the scattering of neutrons due to the motion of the molecule. The molecule is moving in the pores of the zeolite, and the neutrons are bouncing off it, being scattered with a very slight loss of energy, or slight gain in energy, depending on how they interact. And the result is a broadening of the elastic peak. This is what's called quens. So it's the analysis of this that's going to give us information about the mobility, motion, the movement of the molecule in the pores. Well, here's methanol in zeolite hydrogen Y. We saw the INS evidence that it was hydrogen bonded, and you can see, very clear on this slide, you can see that the different values of Q, because remember we can collect the spectrum at different angles, which gives us different values of Q. The line is broadened. The sharp thing here in red is the resolution function, and there is a broadening here which depends on Q. At different angles, there's more or less broadening. That's the sort of information that this one says. So if we measure the half-width of the line versus Q, that'll tell us how fast the molecule is moving. And if we look at the dependence of the intensity, integrated intensity of this broad component versus Q, that tells us the kind of motion that's taking place. Here, for example, is how we plot the half-widths of that Lorentzian component versus temperature versus Q at different temperatures. So as we go up in temperature from 300 Kelvin to 400 Kelvin, the line gets broader, but they're linear with Q squared. Plot the half-width versus the square of Q, we get a straight line. And that suggests a particular model of diffusion, which is so-called Fickian diffusion. We won't go into the details of that. However, if we put methanol into a fresh ZSM5 catalyst, 325 K, just a bit above room temperature, we see no broadening at all. This is a series of spectra at different values of Q, and all we're seeing there is this sharp resolution function. There's no broadening at all. In other words, on the time scale of the quens experiment, down to 10 to the minus 12 seconds, the methanol is immobile. That could be because it's dissociated, of course, forming a methoxy group. But it could also be because it's very strongly hydrogen bonded. We can't distinguish that from the Quent experiment. But the methanol in this zeolite is not moving, whereas in hydrogen Y it was. The hydrogen bonding in hydrogen Y is weaker than in ZC5. Now let's do a reaction at low temperature, like 200 degrees C. So we run the reactor at 200 with methanol, and then we see what we've got. Now at this temperature we don't make hydrocarbons. This is below the threshold temperature for making hydrocarbons. All we make at this temperature is dimethyl ether. And this INS spectrum we can interpret as being due to hydrogen bonded dimethyl ether. We've totally lost the zeolite OH groups, which are here. We're seeing CH stretching vibrations. Down here we're seeing CH3 bending modes, CO stretching vibration associated with dimethyl ether. And this is the chemistry that must be taking place. We've got to be dissociating methanol, reacting with another methanol to make dimethyl ether. That's clear from the INS and from the analysis in the mass spectrometer, or the GC, of what's coming out of the reactor. 200 degrees, methanol being converted to dimethyl ether. If we go to 350 degrees C, we start seeing steady state production of gasoline in the reactor. This is mass spec traces, which are probably quite hard for you to see. What I'd like you to notice though is that initially, so this is the first few minutes of reaction. This is day 1, day 2, day 3. Here we've got a steady state. Mass 55 is butene, mass 91 is aromatics, mass 41 is propene. We're making steady state production here of gasoline range hydrocarbons, light olefins and aromatics. Initially, there's an induction period. You see initially there's dimethyl ether coming out first and then going down, propylene coming up, and then aromatics forming. This is the initial stage. And here's the liquid products that we catch and analyze offline, and they're a mixture of benzenes, methylbenzene, trimethylbenzene, tetramethylbenzene, and substituted naphthalenes. Well, in the reactor we can stop after 3 days and we can stick it into the neutron source and see what's there. That's what we did. So, again, these spectra have been recorded on different instruments, so you can see different frequency ranges being displayed and different resolutions depending on what instrument was used. But look at the high frequency end first, 2 different instruments. We're still seeing some hydroxyl groups from the zeolite. Not a sharp band like you see in the infrared because of the poor resolution, but this is the residual OH groups. This catalyst is still active. It's still converting methanol to gasoline. It's lost some of its acid sites, but it still has a number left. We can see that. These are CH stretching vibrations, and we can distinguish between aliphatic CH3 groups, CH groups below 3,000 wave numbers, and aromatic CH groups above 3,000 wave numbers, and they're resolved in this instrument and one resolved in this one. And then in the low frequency region, we see vibrations again typical of methyl groups and of aromatic species. We run a number of model compounds to compare the spectra we see in the zeolite with model compounds to try and deduce what species are there. The bottom spectrum here was actually obtained by putting dimethyl ether into the zeolite rather than methanol, but it's actually very similar to what we see with methanol. And the model compounds here were durine and orthoxylene, and the closest comparison we have is with orthoxylene. Not identical. What we actually have, of course, in the zeolite is a mixture of molecules, but on average they look like orthoxylene. So methyl substituted aromatics. No particular surprise there, but this is the first time this had been done with a working catalyst, an industrial catalyst. And only neutrons could do that. If we go to 400 degrees, the catalyst continues to work at 400 degrees. It actually has a somewhat different composition. If we look at the spectrum at 400 degrees, we see fewer methyl groups and more aromatic. If you look at the profile of this band compared with over here at 350 degrees, and if you look at these bands relative to these, we can see some differences, which suggest that at 400 degrees we're making hydrocarbons which are less methylated and more polycyclic aromatics. Again, the catalyst is still active, so this is a live catalyst, not a dead one. Now we do quench experiments, and what we do is we take the used catalyst and put methanol into it to see how well it can diffuse in the used catalyst. Ultimately, if the catalyst was completely dead, we would expect it to be blocked. No methanol would be able to pass through it. So what we wanted to do was to see if we could probe how much empty space there was still in the catalyst with methanol. If we compare here the Quen spectra of the fresh methanol in the fresh zeolite and methanol in the catalyst reacted at 350 degrees, you see they're identical. We said earlier that if we put methanol into the fresh zeolite, it's not mobile at all. There's no broadening. Likewise, there's no broadening here in this spectrum of methanol from the catalyst that reacted at 350 degrees for 3 days. But if we take the catalyst which has been reacted at a higher temperature and put methanol in, now you see the Quench is broad increasingly. And we know why that is, because at high temperature, we're making hydrocarbons from methanol, we're producing a lot of water. And water at 400 degrees will start to react with the zeolite lattice and cause hydrolysis. Steam will generate mesopores in the zeolite. And we can show that by the conventional way of doing surface area and pore volume analysis. And you see here that when we go to 400 degrees, we've generated a significant mesoporosity in the zeolite. So the mobile methanol in the 400 degree sample is methanol moving in the mesopores. It's less strongly bound than it is in the small pores of the fresh catalyst. Right, well, if I might have another couple of minutes?
Yes.
Yeah, okay.
Take our time.
Well, okay, thank you. Something different. Some catalysis we were not expecting. This is quite a different project. We wanted to put 1-octene olefins in general into the zeolite at room temperature to study their mobility. How do they diffuse through the zeolite pores? So we put 1-octene in at room temperature and discovered that it wasn't 1-octene anymore. This was a surprise. Let me show you what I mean. Here's the spectrum. This is now inelastic neutron scattering, so vibrational spectra again. Here's the spectrum of the black zeolite. There's the OH groups. Again, very clean spectrum. With this spectrometer, we can see all the way down to 200 wave numbers very clearly. There's almost nothing there. If we absorb 1-octene in the zeolite, that's the red spectrum, then of course we see all the vibrations of the 1-octene, which contain hydrogen. That's most of them. But it doesn't look like the spectrum of pure 1-octene. Here's the spectrum of 1-octene by itself, the zeolite. And you can see we've lost a lot of the vibrational modes. In fact, the modes that we've lost are those associated with the olefinic part of the molecule. We've lost the CH bending and stretching modes associated with the olefin part of the molecule. So it's gone in and it's making something else which isn't 1-octene. Now, you might notice that if we just looked at the CH region, we were doing infrared spectroscopy on the system, that looks almost the same. We might have just guessed from looking at just the CH stretching region that 1-octene was 1-octene. But when we look at the low frequency, we can see something has happened. Some chemistry has taken place at room temperature, which has changed the nature of what's in the zeolite. And the same thing happens with propene. We put propene in at room temperature. Again, this is the octene spectrum over here. For comparison again, this is propene. There's the blank zeolite. There's the propene. The red one is propene put in at room temperature. This one was exactly like the red one here. So propene and 1-octene are making essentially the same thing at room temperature when we put them in the zeolite. If we, however, do an experiment of absorbing the propene at lower temperature, then we see something different. So the blue trace here is propene which has been absorbed not at room temperature, but at 140 Kelvin. When we look at that spectrum, you see that we've got back the vibrations which are due to the olefin. carbon-carbon double bond, and out-of-plane bending modes of the hydrogens, the olefinic hydrogens. In particular, these two have come back. If we put propene in at 140 Kelvin, propene at room temperature, they're not there. Well, we can take that one step further and put in propene at low temperature, and then gradually raise the temperature and see at what point the spectrum changes. Measure spectrum at each temperature, of course, so it takes a long time, taking still 5 or 6 hours for each temperature. So that's displayed over here. Maybe keep your eye on this peak here, which is an olefinic CH deformation mode. Propene at low temperature has that mode. As we raise the temperature, that mode disappears. By the time we get to 293 Kelvin, it's gone. The same is true of 1 or 2 other modes there too. This one here, for example, which is also associated with the olefinic part of the molecule. So the conclusion we reach is that above about 255 Kelvin, propene is oligomerizing in the zeolite and forming long chain CH2 oligomers. And the vibrational spectrum of them is consistent with basically linear chains rather than highly branched ones. We do that by comparing the number of bonded compounds and also with some theoretical modeling. And 1-octene does the same thing. So at room temperature, the zeolite protons are active enough to be able to cause oligomerization of the olefin at room temperature. We did quench experiments as well to see about the mobility of the 1-octene. Here's the half-width quench line as a function of Q at different temperatures. It gets broader as the temperature goes up, as you'd expect. And we could deduce diffusion coefficients from that data. And we could also, by fitting the curves to a model, conclude that the nature of the mobility was actually the methylene groups in this long chain hydrocarbon oligomer, the methylene groups wiggling. Fit the data to that particular kind of motion. So the molecule itself is a long chain oligomer which is stuck in the zeolite pores, but it's wiggling. And that wiggle is responsible for what we see in quench. Okay, well that's the last of my examples. The students, I'll give you a reference here to a review article written recently by some of my collaborators. That's a review in chemical communications, and I refer you to that for more examples of how we can use neutron spectroscopy as a tool in catalysis. And I'll stop there. Thank you.
Thank you very much. Very interesting talk. I believe I also almost had an opportunity to use neutron in Oxford to study crystal structure.
Diffraction, yes.
Right.
Yes.
So metal-organic frameworks. So I had an opportunity to visit the work done work with Richard Walton.
Oh yes, of course. Right.
Okay. Anyway, so I believe we have a lot of questions for Professor Howee, so I'd like to invite some groups. Yes. In the back. Do you need a microphone? No.
I don't think so.
Okay.
No. Thank you for this chance. My name is Asman Kumit from Department of Chemistry, Universitas Indonesia. I have some questions to ask about regarding your slides, your presentation. First is you explain about the principle of neutron scattering, and you explain about the momentum. And I want to ask about the driving force about this theoretical aspect. What is the driving force? And you said that it's different from the quantum theoretical momentum.
Okay.
And you will answer. And I have 3 questions.
Okay. Maybe let me take them one at a time, otherwise by the time you finish I've forgotten. Okay. So you're asking about maybe the driving force. I think you mean perhaps the mechanism. So here's a vibrating molecule, right? Just think of 2 balls on a spring vibrating. Now, when a neutron comes along, it collides with that, and it makes the spring vibrate faster. It bounces off. It's given up some of its energy to the vibrating nucleus, and it bounces off with less energy than it had to start with. Okay? Now that's quite different from infrared, where you have an oscillating electric field associated with the incoming radiation, which interacts with an oscillating dipole moment to cause infrared absorption and a transition from optic beam to beam one. It's a quantum mechanical interaction. The selection, the intensity is determined by the transition dipole, which is depending on the wave functions of the ground state and the excited vibrational state, and the dipole moment operator. So it's all quantum mechanics. In the case of neutron scattering, it's just physics. Right? Just one ball bouncing off another one, causing a change in momentum and a change in energy. So just think of a billiard table, bouncing balls off of the billiard table. The neutron bounces off and is lost energy, and has also changed direction because it's had a collision with that nucleus that it sees in the molecule. That's the difference. That's why I say no quantum mechanics involved. Okay, that was the first question. What was the next one?
The next question is about the lifetime of the catalyst in a fixed bed reactor.
Yes, sir.
And you've mentioned that you observe the cycle process and like the deactivation. Is it like online measurement in that system?
Oh,
like
yeah,
the
yes,
neutron spectroscopy
yes,
for measure the deactivation or something? And what happens after the steady state conditions found, and can the catalyst can be used again or like recycle again to use it?
Yeah, I mean the fixed bed methanol to gasoline process on the commercial plant as it operated in New Zealand would run in a fixed bed reactor for 1 to 2 months. At the end of that time, what happens there is you've got a very big, deep bed of catalyst. Methanol comes in the top. Initially, it's the first part of the bed that is active. And then the reaction front gradually moves down through the bed. As this catalyst deactivates, further down it's still active. And eventually, the whole bed is deactivated. And then it stops making gasoline. At which point, they take it offline, they flow oxygen through it, regenerate it, and then they start it again. Now, we wanted to try and mimic that in our system, but we were not patient enough because we waited for 3 days under our conditions and it was still active. It wasn't deactivated at all. So we stopped at that point and did the analysis. We've since then done more experiments, which are still being analysed, where we've run for longer periods. We can get the catalyst to deactivate it. And then we can collect spectrum of the catalyst, which is no longer active. But in our little reactor, not so little, but in our laboratory reactor in Harwell, the lifetime is not as good as the commercial process, but it's a few days, or a week, or 10 days. Then the catalyst will stop. But it can always be regenerated by just flowing oxygen through to burn off the hydrocarbon deposits, and then it becomes active again. And in the plant in New Zealand, they could do this many times before they had to replace the catalyst. Every time you burn off the catalyst, you're generating steam, and that does gradually destroy the zeolite. So you can't recycle 100 times. You can recycle maybe 10 times, and eventually the catalyst will be dead. It must be replaced in a fixed bed process. Okay? That was your second question.
Yeah,
Now,
the third question, the last question, about the mobility study of the methanol in catalyst. You've explained that you use like 350 degrees C and 400 degrees C for 3 days. And I want to know what will happen if I use the above 400 degrees C, what will happen? And what is the purpose of doing the mobility study? And I mean, I want to know what is the mechanism if I want to study the mobility of this catalyst.
Yeah, the purpose of this was to see if methanol could still move if the catalyst is partly deactivated. Okay. The question is, where does the deactivation take place? Are you blocking the pores at the outside of the zeolite so that the methanol can't get in? Or are you forming coke deposits in the interior of the crystal? So we thought if we could study how methanol can access the used catalyst, we might learn about that. So what we've discovered is that if we use catalyst at 400 degrees, we're actually making the pores bigger because we're partly steam eliminating the zero, and that's what we learned. But methanol is not a great probe because it's also reactive. Even if we're only putting it in at room temperature, it can still be, it's a little bit too strong. And we're now going to do those experiments with methane. Methane will not react. We can look at the mobility of methane. We just want to learn about how much empty space is still in the zeolite that's available. We should put in a molecule which is less strongly bound than methanol. But we didn't know that when we started. So now we're looking to do that. Okay. But the purpose was to see how much pore volume is still available in the zeolite when it has been partly deactivated. Eventually, when the zeolite is completely dead, the pore volume is zero. And then, of course, nothing will go in. That's a completely deactivated catalyst. The pores are completely blocked. And where we have a partly deactivated catalyst, we wanted to see how much methanol can still go in and be mobile. But it turned out, as you saw, that the methanol really doesn't like to move very fast in the zeolite at all. Even in the clean zeolite, it doesn't move. So it was the wrong choice. We should use a molecule like methane, which doesn't interact at all with the zeolite. Then we can study its mobility and learn how the presence of hydrocarbon deposits in the pores might slow the movement of methane through the zeolite.
So it should be seen the mobility by using the hydrocarbons.
Yes.
For example.
Yes. Yes.
Okay, thank you.
Okay, I believe we have time for one more question. Yes.
Yes.
It's nice work, I think. Questions with the static field. Because I'm working also with conversion of carbon dioxide right now, and we always like have a problem with the static field, the efficiency of the products and product that we want. So you purchase from methanol to hydrogen. Is it just one type, or there are several types?
Well, using ZSM5 methanol, what you get depends on the conditions under which you run the experiment, run the reactor. If you flow the methanol through very fast at high temperature, we tend to make quite old things. We were running under conditions where we wanted to make gasoline, so we slow down the flow rate and run at a slightly lower temperature, and we make a mixture. But there are other processes that are more selective for making light olefins. For example, there's the methanol to olefins process, which is not Mobil's process, it's a UOP, American company. And they use a smaller pore zeolite, a Sapo 34 zeolite, and that is selected to light olefins. So if your goal is to make just light olefins, you wouldn't use Edison-5. You'd use a smaller pore zeolite, because in the smaller pore zeolite, pores are not big enough to make aromatics, so it stops at light olefins. So the chemistry is sort of similar: methanol, dimethyl ether, light olefins. In ZSM5, the light olefins go on to make aromatics, but in smaller pore zeolites, you stop at light olefins. So your selectivity depends on the zeolite you use, pore size, but also on the temperature and the flow rate at which you're feeding the reactor. Those are all the variables that affect the selectivity.
It needs time for the coupling.
I'm sorry?
So it needs time for the coupling rate, so like methanol or something like bigger.
Yeah, the residence time, if you like, the flow rate will determine the residence time of the catalyst. So if you allow the methanol lots of time, it'll react further. If you flow very fast through the catalyst, then it stops.
You study about the pressures.
The pressure as well. Now, we haven't really studied that, but the pressure in the working plant in New Zealand is not all that high, only a few bars. It wasn't a really high pressure process. I'm not sure what happens if you increase the pressure. I don't know. In the lab, we don't like to try it.
Right.
Thank you.
Yes.
Will the reactor, do you think the reaction will work with ethanol feed?
Yes, it does. It does. In fact, this is an interesting point because if you have source of bioethanol is a way to turn bioethanol into white olefins, for example, or into gasoline. You want to make gasoline. So yeah, the chemistry maybe isn't identical. It hasn't been studied anything like as much. In fact, one of our ambitions is to study that as well, because we know about the increasing availability of bioethanol, and this tells us we're also convert ethanol into hydrocarbons. In fact, Zedison-5 will convert almost anything into hydrocarbons. People have put all sorts of weird molecules into Zedison-5, and out comes gasoline. Any product of biomass conversion, if you get it into Zedison-5, you'll probably end up making a mixture of hydrocarbons.
The reason I ask is because I'm also doing conversion of some kind of like small molecules. But the questions that the funding body always asks, what is the value, what is the techno-economic analysis of this soil selection? Then actually small molecules, I mean, they have no, I mean, it's valuable, someone is valuable, but they don't really see, like, if I can convert it to something else that has a little bit of value.
Yeah, well, the short answer is yes, you can make gasoline from ethanol. As someone who likes to drink ethanol, I think that was a waste, but that's another story.
Yes, but it is, I mean, by itself, this reaction is economically viable, because you said there is a plant in New Zealand.
Yes, well, the plant in New Zealand, okay, if you're making a methanol from natural gas, you have to go through steam reforming, and that's expensive. So the process in New Zealand is to take natural gas, steam reforming to make synthesis gas, synthesis of methanol, then methanol to gasoline. So that was the steps involved in going from natural gas to gasoline. And the problem economically was that the operators of the company that runs the plant found they could make more money by selling the methanol than they could by selling the gasoline. Okay, so they stopped making gasoline about 10 years ago. So now they make methanol and then just sell the methanol, and they make more money that way. So it's economics. But as I said before, in China now they've built plants to make methanol from coal, and then convert the methanol either to olefins or to gasoline using this kind of technology. So it's all economics. What's the market for gasoline? What's the market for methanol? What's the market for olefins? You can change these processes to match the market to some extent.
Alright, sorry I have to stop
Yeah,
you
yeah,
right
yeah.
there because
Coffee.
unfortunately the time is running out because we have another sessions afterwards. So let's give Professor Howee a big round of applause once again. Before we end up this session, I would like to invite Dr. Fangini to our research and community engagement manager of the faculty to give us a token of appreciation to Dr. Howee.
Too late, Yuri.
Yeah.
Too late. Too late.